Okay, we have a beam here. I'll rotate on a really good set of bearings. But of course, it's as expected, eventually going to slow down and come to rest, at least for a short time. Every time the magnet is pointing at the class or the individual in the class, we made a mark. Okay. Each individual made his own mark, his or her own mark. Different people were at different positions in the class. So not everybody would have had exactly the same information, but it's going to be very close to the same. And the differences in the information will be of interest a little bit later on. Anyhow, every time this magnet is pointing at the camera, we would make a mark. We ignore this one. Now the difference between this magnet and this one is position with its axis horizontal. Well, with its horizontal axis perpendicular to the axis of the beam. Now the way this was done, well, we'll take a look at that. Now the data we took was based on a timing governed by a pendulum that's hanging over there. Every time the pendulum completed an oscillation, the instruction was make a mark like this. Okay. So the first four oscillations, I called out mark, 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 mark. This went on for about 5 minutes. We made on the order of 250, sometimes even close to 300 marks. Every time the pendulum pointed at a person, they would to X. And then continue on, don't miss any marks. So we had mark, marks, mark, 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 X, mark, mark, marks, mark, 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 and so forth. Okay. Then we put numbers on these X's. There were 4 marks before we saw this X, so say at the time was 4 oscillations of the pendulum. Then there were 1, 2, 3, 4 more. There's 4. There's 5th, 6th, 7th, 8th, 9th. So we have a 9 here. And then 10, 11, 12, 13, 14, 15, 16, 17 marks. Then we would make a table. Now, this is the table we used as an example in class. But corresponding to the marks I have here, the pendulum was pointing and had completed another revolution after the 4th, 9th, and 17th mark. So we say at time 4, well, that would have been our first observation, first complete revolution that we observed. So we're going to say theta is 2. Theta is the angle of this thing measured in revolutions. So if theta is 2 revolutions, well, that's our first observation occurred at time 4. 4 oscillations of the pendulum, 47 centimeter pendulum roughly. Then the next mark occurred after, the next revolution was completed just after the 9th mark, between the 9th and the 10th mark. All the second revolutions completed between the 17th and 18th marks, after the 17th mark, and so on. So we make a table of this nature. That table is much longer because we have probably 40 or more revolutions of the pendulum over a period of 4 or 5 minutes. Okay, got a table. Then we constructed some graphs and did some analysis. We'll get into that. For now, I'm going to put the camera on the rotating beam. And we'll do that off camera. Hold on, we'll pause the video here for a second. Okay, there's the beam still moving, but I'm going to give it a good start here. So if you wanted to take data, it's the same system as before, you could. Now I'm just going to leave the camera on this thing till it comes to rest. And there's no need for you to watch this unless you're taking data, because of course, if you were in class, you would already have taken the data. And if you weren't in class, well, this is your chance to take some data. Okay. Now, if you weren't in class, or if you're timing this at home, you don't have the same pendulum we use. You can time it in seconds. Every time the thing completes a revolution, just use your mouse to stop the video. You can read the time at the bottom of the screen, the bottom of your video, and record it. So you know at what time each revolution was completed. There's going to be some error in that, but the errors in this case will smooth themselves out very nicely. I'll say another thing, and then you can just watch in silence. I'm going to save that comment. We'll just let this thing go. Okay. I think I didn't record that, so you're going to have to start it again. Anyhow, this is here if you need to take data. You can always take data by using the time at the bottom of the screen in YouTube. You get the number of minutes and the number of seconds. You can always pause the thing every time this is pointing at you. Now, I've had an assigned for you to do that. If somebody comes into the class late, isn't here, they'll have this to use. You can take data from this. So I'm going to give it a start and we'll see what happens. Okay, we appear to come to rest. So I'm going to give this. So we're going to stop the video. Okay, so from your sequence of marks and X's, you can get a graph of theta versus t, where theta is in revolutions. And t is in cycles of a 47 centimeter, approximately 47 centimeter. Next thing is the graph. Theta versus t. After the information I have here, I've only got 3 data points. So there are going to be 3 points in my graph. They're going to be potentially 40 points in your graph. In my case, t goes up to 17 seconds. So I'm going to put 16 here. 16 because I can easily divide 16 in half to get 8. Divide that in half to get 4. And this interval divided in half. We're going to get 12 seconds at that middle interval. And then we can do smaller increments if we wish. So each of these four cycle intervals can be divided in half to give us 2 cycle intervals. And we can divide each of those in half. We get 1 cycle stretch. And 1 cycle interval over here will give us our 17, because of course we need 17. For theta, well, it's 0, 1, or 2. So we start with 2, we cut that interval in half. My 1's a little bit high there, but you get the idea. We want to do this somewhat carefully with a hand-drawn graph. See the progression of the data. And now I can grab my points. T is 4, theta is 0. So there's a point at 4, 0. And there's a point in T is 9 and theta is 1. So 9 occurs here, 1 occurs here, so point 9, 1. And the graph. So I can actually label these points. You're not going to want to do that with the data. Well, actually, in some circumstances, you might. But I'm just going to label these points so everybody understands. So there's 4, 0. There's 9, 1. That means after 9 cycles of the pendulum, we completed 1 revolution. And then after 17 cycles, we will have completed 2 revolutions. Now, if we draw a curve at these points, a smooth curve, we see the curve is concave down. That concavity indicates the curve's getting less and less steep. It indicates that for a given time interval, we're getting fewer and fewer revolutions, or it's longer and longer between revolutions. So the whole graph will eventually level out and stop at some point. Okay, so if we have that graph, I did quite a bit in class and just kind of summarizing. So let's look down here. The first thing we did was we put a bunch of points in the graph. Now, if you've got 40 points, it's kind of tedious to mark 40 points. You might only mark every 4th point to give you 10 points on the graph. Okay, you'd still get a good curve, and it would still be pretty close to the curve that you would get if you graph all 3 points. Of course, you can also put your table pretty quickly into Excel and create a graph. And that's a useful thing to be able to do. We'll talk about that later. So now we have this white graph here. You can ignore anything that's not in white, although it's kind of hard to ignore, I guess. Just with this graph, I asked the question, how much change in theta between t = 60 and t = 80? between t equals 120 and t equals 140, between t equals 200 and 220. Well, in some detail, I went to the t interval 60, 80, the closed interval 60, 80. Now that's notation that should be familiar to you from pre-calculus and even before, but that means the time interval from 60 to 80 cycles of the pendulum. How much change in theta? Well, theta is your number of revolutions. Okay, so we say, well, the t is 60. But we marked t equals 60 right here. There's 20, 40, 60, 80. There's t equals 60. Come up to the graph and we estimate that the theta coordinate is about 19. Now I created this. To scale the graph, I took 320 and subdivided it to get 160, subdivided this interval to get 240, subdivided this interval to get 80, and then subdivided each of those intervals so that I get a pretty good, pretty accurately scaled graph. I did the same thing with the interval from 0 to 64. Nobody observed more than 64. Most people observe around 50, give or take, revolutions. So I've got a scale here. So at this point represents 60 cycles of the pendulum, and that I estimated to be about 19 revolutions. This is 16, this is 32, then this is 24. This is a little closer to 24 than it is to 16. So I probably should have estimated 21 or something like that. In any case, I made an estimate of theta then for t equals 80. T equals 80, the graph appears to be about here, and theta appeared to be about 22. Now, it turns out those weren't really great estimates, but illustrates the process. So we then say that on this interval, the change in t, which is represented by delta t, this should be familiar notation, was 80 minus 60 or 20. Now that's 20 cycles of the pendulum. Didn't mark it here, but 20 revolutions. And delta theta was 22 minus 19 equals 3. It's actually 3 cycles of the pendulum, or 3 marks. So I use marks for the time interval. The time interval, a single mark, corresponded to a complete oscillation of that pendulum. Okay. So the average rate of change of theta with respect to t was change of theta divided by change in t. Okay. So change in theta divided by change in t was 3 revolutions and 20 marks. So the rate of change, average rate of change of the 3 revolutions divided by 20 marks, which comes out to 0.15 revolutions per mark. I commented that that's the same as a revolution that corresponds to 360 degrees of rotation. So that's a revolution is 360 degrees. I replace revolution with 360 degrees. You can do a little arithmetic and see if that's 54 degrees per mark. You don't have to follow an algorithmic procedure to change the units. To move one set of units to another. Now, in a more complicated situation, we might well want to do that. What I want to talk about, it's 300, we multiply this by 360 degrees per mark per revolution, and so forth, and do a little bit more calculation. Anyhow, this should be obvious. If we're doing 0.15 revolutions per mark, then we're doing 0.15 at 360 degrees per mark, 54 degrees per mark, on the average from this time interval from 60 to 80 marks. And that can also be written as a revolution is the same as 2 pi radians. I'll caution people, you need to know what a radian is, and you need to know why there are 2 pi radians in a revolution. It's going to be very important. If you don't understand deeply what a radian is, you're just going to be following formulas without understanding what they're telling you. Okay. So we do the calculation of radians, we get 0.3 pi radians per mark. And we could approximate 0.3 pi, that's like a 10th of a radian per mark. Okay. Now, if I want to find the rate of change at t plus 100 instant using the graph, take a straight edge, lay it across. It looks like my straight edge wasn't all that straight, but I think it ended up about where it should. And do a tangent line. That should be familiar from calculus. So at t plus 100 is here, and here is the point of the graph, and here's a tangent line. I extend the tangent line for good ways so that these points here that I'm going to use to estimate the rate of change are pretty far apart. So I can get a more accurate estimate of the rate of change. Okay. Well, this point looks like it's at theta equals about 13. And this point looks like it's at about theta equals 46. I chose this point so the t was 200. And this point, of course, t is 0. So t goes from 0 to 200 here. T is 200. Halfway between 160 and 200. Then I calculate the change in theta from this point to this point. That turned out to be about 46 minus 13, about 33. And the delta t from here to here was about 200 marks. So we have an average rate of change using the tangent line of 33 revolutions divided by 200 marks on 165 revolutions per mark. That's the estimate we get of the instantaneous velocity at t equals 100 according to this graph. This graph is cruising fine, and the estimates aren't all that good. It turns out that your average rate of change between here and here ought to be greater than your rate of change t equals 100 because this whole interval occurred before t equals 100, and the thing is slowing down. It's not consistent with what we got here. We got 0.15 revolutions per mark here because I didn't make a very good estimate of especially of this one. So if you use a little common sense, you know that this and this can't both be right. Okay, can't both be accurate. Still, if you get a good graph, you do a good job of sketching the curve, do a good job of tangent line, and make accurate observations, which you can do if you make a pretty big graph and draw it carefully. So you can even use graph paper. Hand-drawn graph isn't going to be as accurate as something you make on graph paper. You're going to get good results. Now, that's average rates of change and an estimate of the instantaneous rate of change. It turns out that to a good approximation, this curve is going to be parabolic. It's going to be a quadratic curve, a quadratic function. It's not going to be exactly quadratic. We'll work a little bit more on why it isn't. Well, that's mainly because of air resistance, but friction is also a little weird. Okay. If theta is given by a quadratic function, then your delta theta over delta t at an instant approaches d theta dt, the derivative, 2at plus b. And it's obvious that the derivative of this exists. And that represents your rate of change of theta with respect to t, which turns out to put with respect to t, and here there's a space, but I hate to leave that off. With respect to t, at time t, is this, so just plug in the time, you know what A and B are. And if you use Excel, you put these points in and do a second degree polynomial fit, a trend line, and you can get the best fit line, the best fit curve to your data. And we're actually going to do that. And if you are inclined, you can go ahead and do that already with your data, because I think everybody got really good data. Okay, so there we have it. And that's the main idea we want to get across. Now there's a little more. There's another main idea. I said that's the main idea. I said one main idea. Okay, if you got a good graph, you can do tangent lines at intervals. And you can estimate the slopes of those tangent lines. So if I do tangent lines at intervals of 50 marks, get a tangent line here at 50, tangent line here for 100, tangent line here for 150, tangent line here for 200. 200 marks if you find 200. I can extend this tangent line. And I didn't want to draw a bunch of tangent lines that they kind of obscure the picture. But to get the slope of this tangent line, you want to extend it quite a ways. So you get like a point here and a point here. Then you could estimate the rise and the run from this point to this point. And this is the slope of the tangent line. That would be an indication of your instantaneous rate of change. It's equals 50. And if you did a good job with the tangent line, you get a pretty good estimate. Then you can do it with t equals 100 and do the same thing, extend this tangent line and estimate its slope, estimate the coordinates of 2 points on an extended tangent line and get an average rate of change. You do that with like 4 points. I might ask you to do it with more than 4 points. I might ask you to do, say, intervals of 40, which give you like 6 points or something like that. Okay. So then you get a table. Now let's just say you went through this process and your estimated d theta dt's, which are the slopes of these lines, were 0.21 revolutions per mark, 0.17 revolutions per mark, and so forth, down to 0.03 revolutions per mark. T, 50 marks, 100, 150, 200, maybe even got 250. So I've got 5 estimated instantaneous rates of change. I can then calculate the change in this rate of change. Now I'm going to give this rate of change a name. I'm going to call it omega. And I'll even just all that now is to say what omega is. Angular velocity. That's a symbol we use for angular velocity. It's how fast it's going through an angle. The angle could be measured in revolutions, it could be measured in degrees, it could be measured in radians, grads, if you know what that is. Usually in calculus and physics, when we're talking about angular motion, we use radians. Now, not revolutions per mark, and be radians per second would be the standard unit. But right now, that doesn't matter. The point is, we can now calculate the changes in the values of omega so that from 20.21 to 0.17 revolutions per mark is a change of negative 0.04 revolutions per mark. From 0.17 to 0.12 revolutions per mark is negative 0.05 revolutions per mark, and so forth. Now we see that these, given that there's some positive uncertainties, there are inevitable uncertainties in our observations. These seem pretty uniform. And maybe it's like 4.5, and this just came out 4, and this came out 5. So there's pretty plausible evidence here, if this is the way it comes out, that this delta omega for a given time interval, because all these intervals in 50 seconds, 50 marks, pretty much the same. So that we can calculate our delta t's, and in every case, the delta t is 50 marks. Time changes by 50 marks from one of these to the next. So that now we can calculate delta omega over delta t. Delta omega is negative 0.04. Delta t is 50 marks. That was 0.04 revolutions per mark. I did something really wrong there. I wrote this down too quickly. This is actually revolutions per mark per mark. which can be written for marks, we're going to talk about that. Okay, so we get negative 0.0008 revolutions per Mach squared, and we divide 104 revolutions per Mach by 50 Machs. We don't expect that applies to the 50 Mach time or to the 100 Mach time. We're going to assume that it corresponds to halfway between 50 and 100 Machs, which would be 75 Machs. So we conjecture that at 75 Machs, this thing is doing about negative, omega is changing at a rate of about negative 0.008 revolutions per Mach squared. And at 145 seconds, negative 0.001 revolutions per Mach squared, because it's negative 0.05. Okay. And we could calculate these. I'm going to ask you to do that probably on 42nd minutes. Okay. These parts under don't mean anything. That's an earlier explanation. Didn't get recordings of all of them. So, okay. So, one other comment here. The omega dt, if you really know the functions, is then the derivative with respect to d theta dt, since omega is d theta dt. And what's that? That's the second derivative. Of theta with respect to t. So right here, we have a connection between the data that we've calculated and some derivatives. That's an important connection, something we want to work on understanding very well at this point. Okay, so that's kind of it. Look for your assignment and you'll get an email.